Hi, Lenny.
Hi there,
You,
Yakir.
you see me?
I'm, I'm really sorry I can't be there. As much as I wanted to come, I'm afraid that the family constraints come first. And my wife's health is not great, and I really did have to be here. I'm hoping that you'll be able to come to Stanford at some point. Jeff said you
Yeah.
might be able to.
Next time I come to the States, I will
Great.
definitely come to Stanford.
Okay, so I don't know how to give this talk except to share screen. If I share screen, I'm not sure you'll be able to see me. I won't be able to see you. But I did want to talk about a couple of things. One of the things is just you and me and our connection many years ago and what I gained from it, the importance of it to me. And the other is a physics concept that's fairly new. It's actually 10 years old. But let me do some screen sharing now. Do you mind if I disappear? Your screen? Thank you.
You can go ahead and screen share. We'll still see you.
Oh, you didn't see?
We'll see it. We'll see you. Yeah.
Right, but I can't see you. Let's see. This always takes me a minute. I've done this a million times. Can you see the screen?
Yes, we can.
Okay. What does it say?
One circle.
I just want to check that it says the right thing. It should say, "Happy birthday, Yakir."
Yes.
Indeed, I do wish you the happiest of birthdays, and I want to thank you. I don't think I've ever expressed before how much I owe to you, and I want to start this talk by spending
Lenny,
maybe, yes.
if you can, we can just see the very tippy top of your head, which is great. But if you can move your camera down.
It's a problem because I can only do this if my screen is lying flat.
Oh,
And in which case I would have to stand.
now we see both of you. Oh,
I know, but I'm standing up and in a very awkward position.
no.
So I'm just going to say, forget seeing me.
Okay.
Just forget. Okay.
Do it away.
Happy birthday and thank you, and I'm going to spend some time saying what I want to say thank you for. The answer, of course, is simple. It's inspiration, which I think is the most important thing that older physicists can give to a younger physicist. And you gave me inspiration that's lasted for, I'm not sure how many years. Well, 50, 60 years, I'm not sure how many since we first met. But let me go back even before I ever met you. I was an undergraduate at CCNY in New York, and I ran into a fellow who was a physics professor there, who was a marvelous fellow. His name is Harry Soodak. Harry Soodak was a very, very good physicist, but he decided to spend his life doing undergraduate teaching at CCNY. He was a very good physicist. He was also a very good professor and teacher. What made him a good teacher was not his great ability to lecture. It was his palpable love of physics, love of the beauty of physics, love of what I would call, he didn't call it, I would call the Einstein way. The Einstein way meant simple thought experiments with far-reaching principles. You know the idea. Einstein started with things as simple as an elevator. A child could understand the experiment, or moving along with a light ray and seeing a static light ray if you were moving fast enough, something which he knew even at the age of 16 violated the principles of electrodynamics. But these very, very simple thought experiments leading to these very, very far-reaching principles. And that's the way Harry thought about physics. Now, at some point, when I was an undergraduate, I was close to Harry, he asked me to look at a new paper and to report on it at a small seminar of some of his colleagues, some of the other professors. In fact, nobody at that time, even at CCNY, knew very much quantum mechanics. I probably knew more quantum mechanics than most of them. What was the paper? Well, I think you can probably guess. The year was 1960. The paper was from 1959. And it was the very famous AP effect paper. They wanted me to explain it, and especially they wanted me to comment on whether I thought it was right. Why me? Well, I was the only one around who knew enough quantum mechanics. I simplified the experiment for them and for myself by making the electrons move along one-dimensional paths, either one way or the other way around the solenoid. It was easier to solve this way, and convinced myself very quickly that for sure the effect was correct. They asked me about that. What did I think of it? It was at that time incidentally quite controversial. Did it violate gauge invariance? Did it violate locality? And I think I said exactly the right thing. What I said was that the effect was both important and deep, very deep, and also in a certain sense trivial. Trivial in the same sense that the Einstein elevator experiment was trivial. It was so simple, it was obviously correct. There was no question of it. You didn't have to really do any hard calculation to see it was correct. And yet, I told them that I thought it might be very far-reaching. I didn't know where it would go, but it seemed like something totally new. In fact, it was my first taste of the Yakir way. The Yakir way was a lot like the Einstein way. Far-reaching conclusions from something almost trivial. And as I said, what I meant by trivial was a very positive thing. I then went away to graduate school at Cornell. This is a picture, of course, of Hans Bethe. And Hans Bethe had a view, at least I don't know if he really believed this or not, but what he said to me and to other students is that profound questions are a trap. Don't get trapped. Don't waste your time thinking about the very, very profound, philosophical, deep, deep questions of physics. That's dangerous. It would be dangerous for your career, and so forth. He was of the shut up and calculate school of physics. As I said, I don't know to what extent he really believed it. I then, after 3 years of graduate school, I went away to Berkeley. And at Berkeley, Jeffrey Chu was the head physicist there. And it was even worse. It was even worse. It was shut up and calculate the X matrix. What's the X matrix? The X matrix is just the amplitude for a pair of particles to come in and a bunch of particles to go off. It's kind of black box. The kind of black box. And the view at Berkeley at the time was you never open that black box. Never look inside the black box. Just use unitarity, analyticity, and Lorentz invariance as a set of mathematical constraints and try to bootstrap your way to the actual value of the S matrix. Most important, never look inside the box. There is nothing other than this S matrix. Well, I wanted to look inside the black box. I wasn't happy with that at all. In fact, I was bored and disappointed by the whole thing. And at Berkeley, I was flailing and failing as a physicist. I hadn't written anything, and it seemed to me that physics was not what I had hoped and what Harry Soodak had taught me it should be. Fortunately for me, a character showed up. You know, there was, I don't know if it still exists, the Reader's Digest. The Reader's Digest, we had to read that in school, and there was always this little thing called the most unforgettable character I ever met. Well, at that point at Berkeley, a very unforgettable character showed up to give a lecture, and it was, some of you will recognize him, it was David Finkelstein. David Finkelstein at the time was a good deal younger than he is here, but he looked like a cross between Paul Newman playing Cool Hand Luke and a biblical prophet. He still did look that way in this. Unfortunately, he died a number of years ago. David and I got to talking. He gave a marvelous lecture. I'll tell you a little more about it, but later. But he gave a marvelous lecture on a subject which turned out to be very important. But for me, the most important thing is he invited me there and then to come to Yeshiva University and to be a professor there. He didn't consult with anybody else. He just offered me a job. I, at the time, was, as I said, flailing and failing, and I immediately said, yes, I will come. I came to Yeshiva University, and I encountered an entirely different spirit of physics than I had at Cornell or at Berkeley. And in fact, I met another very, very unforgettable character. This one I think you know. You probably also know David, or knew David, some of you. Yakir. And that was a big turning point for me. It was finally back to the Einstein way of thinking, and the Yakir way. The deep principles, the paradoxes, the beauty of physics were not a waste of time. They were, in fact, the whole point. And so I came under the influence of Yakir, a younger physicist. Now, we were both pretty young. I think Yakir must have been in his early 30s. I was about 26 years old. We were both pretty young, but I saw Yakir as an older physicist. And I came very much under his influence. By 1967, we were working together and writing papers together. We wrote a paper on what was called the charge superselection rule. But what this paper was really about was about quantum reference frames and entanglement. The relationship between the things which are localized relative to reference frames and the physical reference frames themselves. Physical reference frame meant rods and clocks and so forth. When it came to the charge superselection rule, it was reference frames for the phase conjugate to charge. And the important thing is these reference frames are real physical systems with energy, momentum, and charge. And an object is localized by virtue of being entangled with a quantum reference frame. These quantum reference frames are an indispensable part of the system. That is what, I don't know whether Yakir taught me that, or we taught each other that, or we taught, but that was an important message of this paper. Let me quote from something that I learned from Yakir. In classical general relativity, without quantum mechanics, we can have reference frames be infinitely light so that they don't gravitate. That's good because they won't influence the system that we're trying to study. In quantum mechanics, without gravity, we can make them infinitely heavy so that they don't fluctuate. But in a world with both gravity and quantum mechanics, the reference frames, the physical reference frames, will inevitably both gravitate and fluctuate and become entangled with the rest of the system. We cannot ignore them. That is what I learned from Yakir in 1967, but the quote that I just gave you doesn't come from 1967. It's from my notes for a lecture that I will give next week on the quantum theory of de Sitter space at the IAS, at the Institute for Advanced Studies. Incidentally, the talk will also be remotely. You can't go there either. So this view of things that, as I said, that I learned from Yakir is very current and very important to our understanding of quantum gravity, cosmology, and what have you. Anyway, during those years at Yeshiva and at Tel Aviv, which I also spent time at, if Yakir was inspiration number one, David Finkelstein was inspiration number two. David had done very important work about black holes. He is the Finkelstein of the Eddington-Finkelstein coordinates, which were a choice of coordinates which made it very clear what black holes were, that the horizon of the black hole was called the Schwarzschild singularity at that time, was not a singularity. You could pass right through it, and that black holes were black holes. They were exactly what we now think of as black holes. quantum field theory. A very prescient paper was this connection between spin, statistics, and kinks, and it really just did have to do with topology of field space. You probably know what this picture is. The picture is a picture of a kink in a one-dimensional field theory. A kink, I won't go into it very deeply, but David had generalized the concept of a kink to higher dimensional spaces, used topology to study them, and had understood some very deep things about quantum field theory from the point of view of topology. The Harlow-Bohm effect is also about topology. Winding number and holonomy, these are concepts in topology. I'll just illustrate them here by drawing various paths that go around the solenoid. If you were doing a path integral description of the AB effect, you would draw all these paths, and the paths are characterized by a topological invariant called the winding number. Anyway, Aharonov and Finkelstein at that time were giving birth to a new subject, then independently of each other, to a subject of topology in physics in general, but in quantum field theory specifically. A subject which was to have enormous impact in gauge theories, manifolds, instantons, string theory, quantum gravity, and more. We also wrote a paper that had to do with topology. It wasn't the topology of space, it wasn't the topology of field space, it was the topology of the group being SU2. The paper is called The Observability of the Sign Change of Spinors Under 2-pi Rotations. It did have to do with the fact that a rotation by 2-pi is topologically distinct from no rotation at all. And here is what we said in that paper. We said if you split a beam of electrons, not two electrons, one electron, but split the beam, and you take one component of the split beam and put it in one box, take the other component and put it in another box. Inside the box, there's a magnetic field. There's a strong magnetic field. And you rotate one of the boxes by 2-pi slowly, idiomatically. The other one you don't rotate. Then, if you interfere the electrons afterwards, the interference pattern will remember the 2-pi rotation. And of course, we now call that the Berry phase. I'll just quote from Michael Berry's first paper on the Berry phase. This phase factor exists for bosons as well as fermions. A special case is the sign change of spinors slowly rotated by 2-pi predicted by Aharonov and Susskind in 1967. So this was another paper that did have impact. The impact in this case was on the concept of the Berry phase. I believe that our calculation that we did in that paper was the first calculation of a quantum mechanical Berry phase. I may be wrong. Yakir and I also wrote a paper on string theory, of all things. Yakir is not known as a string theorist. I'll just tell you very quickly what it was. I think this was sometime around 1971. Let's see, 1971. Early in the history of string theory. Strings could always be thought of as collections of little partons, little particles, arranged along a one-dimensional string. There was bosonic string theory, in which these little particles were bosons, just ordinary bosons. But what Yakir and I think and Aaron Kasher proposed is that we could also think of a string theory in which the strings are fermions and which carry spin a half. Each little particle would have spin a half, and that would mean that spin waves could propagate up and down the string. The spin waves, antiferromagnetic spin waves, could propagate up and down the string and add more modes to the motion of the string that were there in the bosonic theory. This reproduced, I shouldn't say gave rise to, it reproduced a theory which was already existing and was not yet called the superstring theory, but it was idea that was already out there mathematically, purely mathematically, without a physical picture. The spin wave excitations gave rise to fermions, the spin, and so forth. Stanley Mandelstam, the great string theorist, attributed the origin of supersymmetries in this paper. I don't think that was true. I think that's an overstatement about the importance of this paper by a lot. But nevertheless, we had a lot of fun thinking about this. Anyway, back to Einstein. Let me come back to Einstein now. This is the second half of this lecture. In 1935, after Einstein was considered way, way past his prime, he, Podolsky, and Rosen published a very important paper. You know what it is. It's a paper in which quantum entanglement, I don't know if it was the first paper where quantum entanglement showed up, but certainly historically it's seen as the beginning of the concept of quantum entanglement. An entangled state, let's say, of two particles, is very unusual from the point of classical physics. The entangled state contains everything that can be known about the system, but nothing about its individual components. That's crazy from a classical viewpoint. How can you know everything that can be known about a system and know nothing about its individual components? That's an entangled state. I'm not going to go into it further than that, except to say this is what Einstein calls spooky action at a distance. Now, entanglement is not action at a distance. It's subject to a principle called no signaling. A signal cannot, Roger talked about this before, entangled systems cannot be used to send information superluminally faster than the speed of light. I think Einstein certainly knew that. But that was the first 1935 paper that I want to draw attention to. There was another paper the same year, in 1935. It was by Einstein and Rosen, the same Einstein and Rosen, without Podolsky. And it was a general relativity paper. The general relativity paper introduced the idea of an Einstein-Rosen bridge, which is today often called a wormhole. It was a wormhole connecting two black hole solutions, two Schwarzschild solutions. It's not said that way in the Einstein paper, but that's what it was. And the two black hole solutions, you could either think of the way they did, as existing on two completely separate sheets of space, or you could think of them as black holes separated by a significant different distance in the same space. These wormholes were such that if you went into one and didn't worry about the constraints of the speed of light, you just imagine you could move as fast as you want, you go into one and you come out the other. That's what an Einstein-Rosen bridge was. What do Einstein-Rosen bridges, so ER, have to do with EPR? Before the year 2013, most physicists would have said nothing. After 2013, which was 78 years after Einstein's paper, many of us would say it has everything. They have everything to do with each other. There's a concept in physics now called ER equals EPR, which says that in a certain sense, these two concepts are the same. This is due to one Malvacener, principally, and myself. One Malvacener was younger than me, but he also played the role of an inspiration for me. And anyway, let me explain what that concept, without proving it, without trying to argue it, without trying to give you a technical explanation, let me just tell you what this idea, this ER equals EPR idea says. Imagine you have space, a big space with a lot of separation between two regions. In one region you have a cloud of particles, in the other region you have another cloud of particles. These clouds of particles have never talked to each other, they've never interacted with each other. There they are. I'll redraw that by folding over the space. Nothing do, I just fold it over so that I can draw them as being close to each other, even though they're not close to each other. Just to get them both on the same page, so to speak. Now let's take those particles and let gravity do its work. Gravity doing its work means collapsing the clouds of particles and eventually collapsing the particles into black holes. What do you get? You get two black holes which have nothing to do with each other. They're separate from each other. I drew them as close to each other, but they're not close to each other. And they are in no way connected to each other. But now, let's do something a little bit different. Let's take a cloud of particles, this time twice as big as the original clouds of particles. The cloud of particles are now at the same place, and they are allowed to interact and become entangled. For example, they could become entangled into a collection of bell pairs. Once they're entangled, let's separate them again. We separate them, and now we have two clouds of particles which are entangled with each other. Perhaps in the simplest way of just being a product of bell pairs. Again, gravity does its work on each component, and each component now collapses into a black hole. What do we have? We have two black holes which are entangled with each other. And by virtue of being entangled, they have a wormhole between them. Now, as I said, I'm not going to prove this to you. This is well documented in the literature. I simply don't have enough time to go into the technical reasons why we believe this is true, but this is one of the things that modern quantum mechanics, gravity, and particularly something called the ADS, the ADS CFT correspondence, and other very modern ideas to much younger people than either Yakir and myself, that two entangled black holes are exactly the object which Einstein and Rosen had discovered as a solution of gravity. A wormhole between them, and that led Juan, Malvicena, and myself to call this idea ER equals EPR. Actually, it was Juan who suggested this name, ER equals EPR. That they are very closely, not only closely related to each other, but in some sense the same thing. Let's talk about the character of wormholes and entanglement a little more. From the entanglement side, there's a no signaling principle. You cannot use entanglement to send signals faster than the speed of light. On the wormhole side, there's a similar constraint. You also cannot use wormholes to send signals faster than the speed of light. It's called the non-traversability of wormholes. It's a geometric fact about wormholes that you cannot send signals through them. What you can do with wormholes is you can send two participants, in this case it's Franklin and Linus, into the wormhole from the two sides and have them meet in the center. But that's completely invisible from the outside because it's beyond the horizons of black holes, so let's not worry about that. What you can't do is send Linus through the wormhole to shake hands with Franklin on the other side. That is the non-traversability of wormholes. Wormholes are non-traversable. Entanglement is subject to the no-signal condition. Now, let me just say a few more words about why, or where, the geometry of this non-traversability. This is just one way of looking at the non-traversability. There are several ways. But if you look at the Penrose diagram for a two-sided black hole like this, you'll discover that the wormhole between them rapidly grows with time. It rapidly grows with time in such a way that if something enters the wormhole on one side, I'm imagining going through a tunnel, driving through a tunnel. If you enter on one side, the wormhole grows so fast that you can never get through to the other side. Even our light ray can't get through to the other side. That's the non-traversability of wormholes. There's a long story that goes with this, a quantum mechanical story that relates it to the growth of quantum complexity, but that's not what I'm here to talk about. Okay, there were two discoveries which took place recently, well, fairly recently, one somewhat older, one somewhat newer, which have to do with this non-traversability and entanglement that I simply want to tell you about. Neither one's due to me or to anybody around me. One of them is due to Gall, Yakir, and Wall of 2017. And it's the fact that indeed wormholes can be made traversable. They have to interact with each other. They can't be arbitrarily far apart, and it will not violate the speed of light constraint. But the way you make wormholes traversable is by constantly sending back and forth information in the form of classical information back and forth between the two ends of the wormhole, sending classical bits back and forth. The classical bits encode no information about what's going on inside the wormhole. It's kind of random. But by continuously allowing the two ends of the wormhole to interact by sending back and forth classical information, that actually retards the growth of the wormhole. And the result is the wormhole becomes traversable. It does not violate the speed of light constraint because you do have to have this interaction between the two ends of the wormhole. And that interaction takes time. So nothing violates any principle here, but it does make the wormhole traversable. What it says is you can send a quantum state into one end of the wormhole, send classical information back and forth between the two ends of the wormhole appropriately, and if you do it right, that quantum state will pop out the other end of the wormhole. Okay, is this something crazy? Yes, it's quite crazy, but it's absolutely equivalent to another discovery that was earlier, the discovery of quantum teleportation by Bennett, Assad, I can't pronounce all the names. Actually, Asher Parish's name is there, the guy named Wooters, from 1993. These are all, actually these are mostly computer scientists, well, quantum computer scientists, not completely. And it's the discovery of quantum teleportation. You probably know what quantum teleportation is, but I will just very quickly remind you. You can use a pair of entangled particles and a pair of entangled qubits, again, to send quantum information through a channel, to hide that quantum information and to send it through a channel. You have to do basically the same things which I described before. You combine the unknown quantum state psi with one of the members of the quantum of the entangled system. You make measurement, and you transfer that measurement as a piece of classical information to the other side, from Alice to Bob. That is a kind of interaction between the two sides, a classical interaction between the two sides, and lo and behold, if you do it right, again, the quantum state can pop out from the other side. Again, this doesn't violate the speed of light constraints because you do have to send this classical information back, but the upshot is that traversable wormholes and quantum teleportation are, in fact, exactly the same thing, with quantum teleportation being a sort of limit in which you're talking about only two entangled particles, whereas black hole situation, you're talking about two highly entangled, huge numbers of degrees of freedom, namely the microstates that make up the black holes. Okay, that's as far as I'm going to go. That's all I'm going to tell you. I'm going to stop at this point here, and again, say happy birthday to Yakir, and especially to thank you for, as I said, for the inspiration that you've provided me that has basically lasted me all of my scientific career. Happy birthday, Yakir, and, well, happy birthday. a little bit. And I think I will try to go back. Unless, well, all right, but any questions that require my screen sharing, I'll leave screen sharing up for a minute, but then I'll, can you see me?
Yes.
Yes.
Yeah, Lenny, we can see you very, very well. Thank you. Spectacular talk. Thank you so much.
Okay, you are.
I understand congratulations are due to you. I just learned that you got the RAP prize, that's correct?
I did. That's correct.
Okay, so congratulations.
Okay.
And thank you.
I wanted the rack prize, which I suspect I would never have won had I not been inspired by Yakir. I might not even be a physicist if I hadn't been intellectually rescued by our early relationship. So thank you, Yakir.
And thank you for a lovely talk. And I really hope that we will get together soon. And
Oh, I hope so.
yeah, and have some interesting discussions. Thank you.
Absolutely. Maybe even write another paper.
Okay.
Any questions? Please come on up. Come on, Tomer, come on up.
Thank you, Professor Susskind, for the talk. Very interesting. I want
Who are you?
to.
Okay, do I know you?
No, I'm a student of Yakir.
Oh, okay.
Yeah.
Oh, lucky you.
He's my non-official mentor for a couple of years now. Yeah. So I just want to ask you, when you consider the ER equals to EPR, so in general relativity, the foundations is space and time. But in quantum mechanics, the space, spatial dimensions, it's not the foundations of quantum mechanics, only in different formulations of the theory. So in your theory, do you say that space...
That's my theory. Wait.
Yeah, in this thing, do you...
Yes, in this
Yeah.
thing, right.
Yeah, and do you find spatial dimensions as that they may have a special role also in quantum mechanics?
They're which are a special role.
The space
Yeah,
and
say it
time,
again.
do they have a special
Yeah.
role in quantum
Okay,
mechanics? Because we can
According to
have
the
quantum
view of
states.
Physics, according to the view of physics, which I know that the string theory, but really doesn't have to do with string theory. I'm for some reason considered a string theorist. I'm not a string theorist. I'm a theoretical physicist, but I do hang out with people who grew up in the string theory world, particularly one I was saying, Whitman and other people like that. But there is a view of physics which is called the holographic view. And the holographic view says that that space-time or space in any case is emergent in a certain sense, in a way in which a hologram, by a hologram now I mean the image, the three-dimensional image of the hologram, is emergent from the little bit of scribbles on the film of a hologram. Two-dimensional world becomes a three-dimensional world. In other words, the quantum information in 3 dimensions is encoded in a certain two-dimensional way. The two-dimensional way is highly quantum mechanical. It describes a quantum mechanical system, highly interacting, and so forth. And the three-dimensional world that it encodes is the world in which ordinary space and time are more recognizable. All of this takes place in that holographic context. So space and time in this view are emergent from the quantum mechanics of this holographic duality. Is that the final word? Who knows? I don't know, but that's one way of thinking about it. So I think your question is, what is the connection between the quantum mechanics and the space-time? understand it now, the view of physics is being pushed by these young people in the direction of space being emergent as a consequence of entanglement and large numbers of degrees of freedom, entangled in various ways in the holographic representation. And that's about all I can say about it now, without having to spend hours going into it. But and I would advise, if you're really interested in quantum mechanics and gravity and their connection, is to become familiar with these ideas that are emerging, and it's true from the string theory community, but which are somewhat independent and really based on quantum information theory. So that's not best I can do right now.
Yeah. Great, thank you.
Hi Lenny, Adi Stern from Weizmann.
Oh,
We had
hello,
some,
Arnie. How are you? I haven't seen you for many
years, right? We had some.
I do follow you some of your work sometimes.
Say it again, please.
I do follow some of your work sometimes.
Oh, thanks. Happy to hear that. Happy to hear that. It's a pity we didn't have now a chance to
Were you
interact
also
here.
a student of Yakir's? Were you also a student of Yakir?
No, I wasn't officially. You know, if you look at the records, I'm not a student of Yakir, but a large part of my PhD works with him.
I didn't mean officially.
Yeah, so it wasn't.
Morally.
Official was not a strong part of my education.
Neither.
So as you know, I'm a condensed matter guy. So I'm asking myself. I was asking myself when I heard your talk, can we get the black holes out of the story? If you say that ER is just teleportation, we don't need black holes for teleportation, and EPR, of course, we don't need black holes for. So either an analog that does not involve general relativity to this equality of EPR equals ER.
Yeah, I think the relationship between the two, well, I'm not sure what you would mean by ER without having some general relativity involved.
Teleportation.
But you know, a connectivity, a connectivity between distant regions of space, which is due to entanglement. Yeah, I don't think it necessarily involves black holes. General relativity and black holes, in this view, are what we might call the hydrodynamics of entanglement. When there's so much entanglement present that the entanglement starts to behave like a fluid and has laws which are almost hydrodynamic in character. Those hydrodynamic laws are the laws of general relativity. That's the view that I would say is emerging. Just like you could have, let's suppose you start with 4 particles in a box. 4 particles in a box don't behave very hydrodynamically. Okay. But they do behave like particles.
Yes.
The same rules of particles, if you add 6 particles, 10 particles, 1,000 particles, at some point begin to behave smoothly like hydrodynamics. I would say the same kind of thing is going on here. Take a small number of particles which are entangled. Yes, you can send information to a channel, which is very similar to quantum teleportation. But as you build up the number of particles, it begins to behave in this hydrodynamic way, which has this general relativity description, and eventually becomes a description in terms of geometric wormholes, where there's enough entanglement to be described in a more collective kind of way. That's what I would say.
So the black hole aspect can be replaced by a fluid behavior or hydrodynamic behavior.
Yeah. Well, it's a fluid behavior which the fluid is itself in some sense entangled.
The fluid itself is?
Entanglement.
I see. Great, thank you very
It
much.
is a tough impact. The words that hydrodynamics of entanglement are not my words. They were due to Joe Polchinski, who's unfortunately no longer with us, but Joe Polchinski once described quantum gravity as the hydrodynamics of entanglement. I think that's a very good way of describing one of the themes of well, I don't know what to call it, of this view of physics.
I see. Thanks a lot. It's an very interesting viewpoint.
Hi, nice to meet you. Yes, I'm Yuta. It's from Japan, working from Japan. Yeah, that's right. Yeah, thank you so much. Very beautiful talk in this ER today. ER equals EPR. In the sense on that you're talking about with that in the beginning, in the initial collaboration with Yakir, in that talking about the reference frame problem. In that I do not understand. In that I'm a little bit confused. ER in the EPR context. In that what is the relationship on the reference frame problem in the context of the ER?
Well, it's one or two different things.
Of course, the different thing, but the EPR.
Well, it's an interesting question to compare reference frames at the two ends of the wormhole.
Yeah.
And the answer is you can compare the reference frames going through the wormhole by parallel transport through the wormhole, or you could compare the reference frames going around the wormhole the long way. And the relationship between those two are the relationship of holonomy. You can imagine transporting information from a reference frame starting at one side of the wormhole all the way around the long way and then passing through the wormhole back to the original starting point. And there will be a holonomy, which means the reference frames will not necessarily be parallel to each other. So you can interpret that either in terms of geometry, or you can interpret that in terms of entanglement. Two ways of thinking about the holonomy of going around and then through the wormhole and comparing reference frames at the same point.
Yeah, but in that case, what is the situation is that in the time on that in the wormhole? It's that we have to define, but it's not well defined in the time in the wormhole. Then that's why that's the trouble.
I'm not understanding what you're asking.
That's the kind of the sharing on that in that reference frame in the wormhole. In that case, we have to well define in that at a certain time. But in the GL, it's not well defined in the wormhole.
What is not well defined?
Yeah, it's not well defined the time in the inside the wormhole. Then
Well, I think time is never well defined unless you have a clock.
yeah,
If you throw a clock into the wormhole, somebody inside the wormhole could use the clock to define time. I would say one of the themes which is beginning to emerge is the importance, and again, dates back to this paper that Yakir and I wrote a long time ago about the importance of reference frames being thought of as physical systems. The importance of actually having clocks, not just abstract clocks, which are just mathematical, but actually having clocks. If you throw a clock into the wormhole, that clock can be used to define time inside the wormhole.
Oh.
For as long as it lasts without being destroyed.
Oh, okay. That's good. Thank you so much. Yeah.
Hi, Ellie. I understand that lately you are also interested in complexity, right?
Yes.
Okay.
Yes, I am interested.
I want to suggest another aspect of complexity that I'm interested in. You know that there is a problem between physics and free will, and people always say that the uncertainty of quantum mechanics does not let you really have a meaningful free will because of the fact that the choices are random, right? I mean, quantum mechanics gives you some options, but the choice between the options must be according to the Bohr rule. So I have an idea. Suppose you come to such complexity of a system that there is no way to make a copy of it. And suppose our brain... Sorry?
There's no way to...
No way to make a copy of it. So suppose I make a decision among the different options, and people want to prove to me that that decision must be according to the Bohr rule. Then they have to be able to make copies of me that will be completely identical and show that all these copies making the decision according to the Bohr rule. But suppose there is no way to make a copy of my brain without killing me, so there will be no way to prove that my decision was according to the Bohr rule. So I say that there is a possibility of some definition of complexity according to the issue whether the system is so complex that you can't make a copy of it, and that will be very relevant to the issue of free will.
I see. Okay, that sounds like a very good topic for us to discuss when you come to Stanford.
Indeed. Okay, so think about that issue of complexity, which is different, of course, than the one you're discussing, but it's an interesting way to define complexity, not by how many parameters you need. I need a lot of parameters to write the Bible, but I can make really a copy of it. But when one tries to make a copy of my brain, the relevant part of it for the decision, I think that there is no way to make a copy of it, and then the issue of the Bohr rule, perhaps it cannot be applied to my brain. So what do you think of this idea? You have to think about it.
I don't know, but I think it is very important at some level to think of ourselves as part of the quantum system.
Mm-hmm.
And if we really can't think of ourselves as part of the quantum system, well, I don't know how we make sense out of physics.
Okay, but...
You're asking, I think, whether there's some sort of threshold in complexity
Yeah.
that somehow free will becomes emergent. I think that's what you're asking.
Yes. No, and I'm saying that's connected with the idea that you can't make a copy of such a complicated system as my brain, and that means that there is no way to apply to it the Bohr rule, because to apply a Bohr rule you need to have many copies. And each time, either in time later when I make the same decision, my brain is different, or you need copies at the same time to make sure that the Bohr rule applies.
So how do we know that the Lord up in heaven, when he created you, did create a large number of copies of you?
No, I'm saying suppose it's impossible to make a copy of me because it's such a complicated system that if you try to take 10 to the 20 for 27 atoms and try to create the whole entanglement that is in my brain, you probably will create a black hole before you can do it.
No, that's beside the concept.
Okay.
But how do we know that there aren't laws, that you're not part of this number of copies of you which were created at the same time that you were.
Yeah, but I'm saying suppose it's impossible. See,
Okay.
The idea is try to make, suppose somebody gives you my wave function and you have a collection of 10 to the 27 atoms in a box,
Yeah.
and you now have to bring a lot of instruments to create that wave function. I think I can prove that you will create a black hole before you will be able to do it. That's my idea.
Okay, I would like to see the proof of that.
Okay, good. That when we meet again in Stanford, I promise to come and then we will discuss it. Okay? Okay.
Excellent.
done.
Anybody else?
All right, Lenny, I think that's a pretty good last question, and I think we've left you with enough time to get to your ceremony, and congratulations again.
Good. Okay.
Thank you so much, Lenny. Thank you.
Bye-bye.
Bye-bye.